So welcome to lecture number 30 of physics optional paper 2. Okay, and in this lecture number 30 we are going to start with a new topic, and as we will move on, you will also be able to learn about the eigenvalues in detail, which had been superficially told in the previous class. Okay, so the eigenvalue concept which was superficially told in previous class will be in fact more clear to you in the forthcoming sessions. But right now we will focus on expectation values of dynamical variables or observables. Okay, so what does it mean by expectation value? Expectation value is basically your average value. Okay, so in quantum mechanics your average value is basically called as expectation value. Okay, so it is the average of the result of large number of measurements on independent systems. Okay, suppose there are some systems which are quantum mechanical systems which are independent of each other. Okay, so you will basically take the average of the result on large number of such systems. Okay, you will basically take its average. Suppose there are 100 such systems, so you will take the average of such 100 systems. Okay, and those systems should be independent of each other. Okay, the same particle is going in every other system. Okay, it should not be like that. The same particle should not go in every other system. For example, if there are 100 systems, suppose, but if the same particle is going in other 99 system also. Okay, if the same quantum particle is going in other 99 system also, then such a system is not independent, it is dependent system. But we are talking about independent systems, means they are isolated from each other. Okay, they are isolated from each other. So expectation value is your average of the result of large number of measurements on independent systems. Okay, so let A be an observable associated with such a system, and A hat be the operator corresponding to A. Okay, let A be an observable, and A hat be an operator corresponding to this observable A. Okay, so A hat is the operator corresponding to this A, and I had already told you that to every observable there is a corresponding operator also. Okay, to every observable there is a corresponding operator also. I had told you already this. So this is an observable, and an operator A hat is there corresponding to this observable A, and your ket psi is eigenstate of each system. Okay, now this is the ket psi is the eigenstate of each of the system. There are suppose n independent systems, then each of these n independent systems will have eigenstate ket psi. Okay, so this observable can be anything. It can be position observable, it can be momentum observable. Okay, anything, any observable. Means like in classical mechanics you see various observables like position, momentum. Okay, so all those are also there in quantum too, also there in quantum also. So this is the thing, and let's move on towards our next slide. So how will the expectation value be defined then expectation value or average value of A or A hat. Okay, actually to be more precise it should be A hat. Okay, to be more precise it should be A hat, but the quantum mechanics in at UPSC level is not so hi-fi. Okay, the quantum mechanics which you are learning for UPSC exam is not that much hi-fi, it is elementary one. Okay, the quantum mechanics which you have in your UPSC syllabus is elementary. So we can say that expectation value or average value of A or A hat. Okay, we can call A or A hat. Okay, but to be precise calling it to be A, expectation value of A is wrong. Instead we should call it expectation value of A hat. Okay, in reality, but at your level we can call it expectation value of A also, so don't worry. So you can call it both. Then expectation value or average value of A or A hat with respect to the state ket psi. Okay, with respect to state ket psi, state ket psi is defined like this, that A hat, expectation value of A hat or A is defined something like this, that it will be bra psi A hat ket psi. Okay, bra psi A hat ket psi. Okay, and divided by bracket psi. Okay, so like this it is written. Now when you expand this notation, when you try to expand, it will look something like this. Okay, it will look something like this. Now this is basically your brass eye. Okay, this is your brass eye. So correspondingly this brass eye will turn into complex conjugate of psi. Your a hat will be over here and your cat psi will be like this. Okay, over here. So why the limits minus infinity to infinity? Why the limits minus infinity to infinity? Because limits are not defined. Over here our limits are not defined. So as our limits are not defined, we will take the limits minus infinity to plus infinity. Okay, so that's why limits are like that. Okay, because we are integrating for the entire universe, as our space is not defined. As our space is not defined, so we are integrating for entire universe. Okay, and the denominator will look something like this. This bra psi will become complex conjugate psi, because by definition of bra notation it is written like that, and this ket psi will look something like this. Okay, so this is quite obvious from your notations. Now let this be equation number 1. Okay, suppose this is your equation number 1. Suppose this is your equation number 1. Then what will happen? If the eigenfunction or vector is normalized, suppose the eigenfunction, your eigenfunction or eigenvector, which is your psi, ket psi, I mean, it is normalized, suppose. Okay, so if it is normalized, then this value should be equal to 1. As this value should be equal to 1, so this value will correspond to 1. Okay, so this value will correspond to 1. So if your eigenfunction or vector is normalized, then the denominator of this expression will become 1. And as soon as the denominator of that expression becomes 1, what do we get? See, I have written here also. Okay, so the expression on the previous slide, it becomes divided by 1. So this will vanish, denominator will vanish, and only the numerators will remain. Okay, so those things have remained, and the numerator has remained, so this thing remained, and this is the thing. And in most of your numericals, okay, not in all numericals, okay, in most of your numericals, your this bracket psi will be equal to 1 in most of your numericals. Most, not all, most of your numericals I am saying. So that's why it is compulsory to check whether psi is normalized or not. In your problem you must always check whether psi is normalized or not. Okay, and if it is not normalized, then normalize it first. Okay, if it is not normalized, suppose this integration does not come out to be equal to 1, then you will have to basically normalize your wave function. Okay, so it will come later. Numerical part we will go later into that thing, but right now the theory is something like this. Okay, so this is basically your equation number 2. Okay, because the denominator has vanished because it became 1. Okay, now consider a very large number of mental copies of quantum system. Each in same state ket psi. Okay, each of them is in the same state ket psi. Now what does this mean? This simply means that you are talking about the theory of multiverse. You might have learnt about universe. Okay, you might have learnt about universe, although this theory of multiverse is not there in your syllabus. Okay, in your syllabus of quantum mechanics UPSC physics optional, this theory of multiverse is not there in your syllabus. Okay, but I am talking about advanced level. In MSc physics someone might have learnt that we have one universe. Okay, and according to some scientists there are multiple such universe. Okay, there are multiple such universes like ours. Okay, and all those universes like others, all those universes like ours, those are identical. Like in the other universe also there will be earth, on other universe also there will be Mars. Okay, same, exactly ditto same thing will be there. Okay, but some of the things will be opposite. Like for example, if you had suppose two choices. Okay, you had two choices. Suppose you had one choice of girl A and another choice of girl B. Then in this universe, this universe on which you are watching the video, you choose to marry girl A. Okay, but it is possible that in another universe you might have married girl B. In another universe, in which there is Earth. Okay, and there is all the planets also, and dicto same universe, but the choice you made is different on that universe. Okay, you make exactly opposite choice on that particular universe. So this is called as basically theory of multiverse. Okay, theory of multiverse. So consider a very large number of mental copies of quantum system. These mental copies of quantum system simply mean that they are talking about multiple universe. Okay, multiple universe. Now each of this universe has the same quantum mechanical system, and they have ket psi as the same state. Okay, each in the same state ket psi. So each of these universe is in the same state ket psi. The observable A is then measured on each system. In this multiple universe, observable A will be measured on each of the system. Okay, each system means the same system on multiple universe. Okay, so observable A is being measured. The outcome of the measurements outcome will be different because these are multiple universe. The way you had chosen different girl in different universe. Okay, the way you had chosen different girl in different universe, similarly the outcome of measurements in different universes will be different. Suppose there are n universes, then on the outcome of universe number 1 is A1, the outcome on universe number 2 is A2, the outcome on universe number 3 is A3, and so on and so forth. Outcome on nth universe is An, and so on and so forth. Okay, so these are basically your eigenvalues. Okay, what will these be? These will be your eigenvalues. Okay, because these are your various outcomes on multiple universes. Okay, so these are basically your eigenvalues. And this theory of multiverse, I don't know whether, but you can search for it. It is a true theory. Okay, it is a true theory. It is propounded by many scientists. So outcome of the measurement are A1, A2, dot dot dot, An, dot dot dot. Okay, and there is nothing in the class which I say just like that. Okay, you can always Google search and satisfy your curiosity whether I told the right thing or not. Okay, you can always Google search and cross check my statements. You will find that never in my class I have said anything wrong. Never. It is a record. Never in my class I have said anything wrong. Never. Okay, it is a record. Never. Okay, so you can always cross check by Google verse. Just go and Google search. Just go and search theory of multiverse in quantum mechanics. You will find the Wikipedia page. Okay, so that's the thing. So the outcome of the measurements are A1, A2, so on and so forth, An, and let these be the eigenvalues. Okay, let these be the eigenvalues. Then what will happen? Then the corresponding probabilities of these occurrence, that in universe number 1, A1 occurrence of A1, okay, then occurrence of A2, then so on and so forth, occurrence of An. These are the probabilities of occurrence of them. Okay, and these are respectively the things. Then the expectation value, how will it be defined? Then the expectation value will be defined something like this, that it will be An Pn summation over n. Suppose there are n such systems, so n will run from 1 to n in case there are n systems. If there are infinite systems, then n will run from 1 to infinity. Okay, but there will be finite systems only, don't worry. In your exam, more than 3 systems will not be there. Only 3 systems will be there. At most 3 systems will be there in your exam, up to A3 P3. Okay, I have never seen that more than 3 systems the examiner has given. Never in your paper such things has been given. Okay, So a1 p1 plus a2 p2 plus so on and so forth. Okay, let this be equation number 3. Now how these values have come, okay, how these values have come, no need to go into the proof of that. Okay, need not go into the proof of that. They never ask such questions. Okay, from this part they have always asked numerical only, and in the future also they will ask numerical only from this part. Okay, so do not remain in fear that what if they ask the proof of this. They will never ask the proof of that, because the proof of this is a part of MSc syllabus, not UPSC physics optional syllabus. Okay, so need not remain in fear. Okay, so your now I had already defined Pn in the previous class. Okay, that when I was defining the eigenstate, then I had defined that Pn is defined something like this. Okay, let this be equation number 4. Then also here ket psi will be like this, and this will be given in your question, as will be evident in this same class. As we will move on towards one numerical, this thing will be quite evident to you. Okay, so ket psi will be equal to c1 ket psi 1 plus c2 ket psi 2, and so on and so forth. Okay, and how will you check the normalization condition? How will you check whether psi is normalized or not? How will you check it? Simply take the squares of coefficients, c1 square plus c2 square, so on and so forth up to cn square. Okay, so c1 square plus c2 square plus c3 square. Okay, so on and so forth up to cn square you will take, and you will see whether it comes out to be equal to 1. If these square and summed up, when these coefficients are squared and summed up. Okay, so after squaring and summing up these coefficients, if the value comes out to be equal to 1, means c1 square plus c2 square plus c3 square plus c4 square plus c5 square plus so on and so forth up to cn square, if there are n such systems, then the values of the sum of these coefficients squared will be equal to 1 if psi is normalized. And if psi is not normalized, then the sum of these coefficients squared, okay, it will not be 1. This expression will not be 1 in case your psi is not normalized. Okay, so it is very easy to check whether psi is normalized or not. Okay, so let's move on towards some problems. Okay, some problems based on this concept. So let's move on towards them. Okay, and before moving on to the problem, you must learn one thing, that this a hat which has been written over here, okay, this a hat which has been written over here, will it be applied on the will it apply on psi star, or will it apply on psi? This is the big question which everyone will want to answer. So let me tell you that for elementary concept, okay, for the time being, for this lecture which is going on right now, this operator a hat will be applied on psi x, because it is written afterwards. Okay, so whatever function will be written afterwards of the operator will apply on that. Okay, so as psi x has been written afterwards of the operator, so a hat will apply on psi x instead of psi star. Why? Because psi x is written afterwards of a cap. Okay, so psi x is written afterwards of a cap, that's why a hat will apply on psi x instead of psi star. So keep this thing in mind while solving the numerical in this particular class. Okay, in this particular class numerical, but never ever make it a rule. Okay, it is not a rule that a hat will always apply on psi x only because psi x is written afterwards of a hat. It is not like that. Sometimes the operator a hat may also apply on both of these, or it may apply on psi star also. Okay, so it is all these things will come in the upcoming classes, on which wave function the operator will apply. All these things will come in the upcoming classes, so you will have to wait a little for it. But in this particular lecture, this a hat will apply on psi x only. Okay, so keep this in mind, because the wave function has been written afterwards of a hat. So whatever wave function will be afterwards of a hat, the a hat operator will apply on that only in this particular class. Okay. Yes, so let's move on towards our problems. So problem number 1 says this. Okay, we had learnt up to here, right? So after a break for a short time, I am making this video once again. Okay, so normalized wave function of a particle is this. Now it is given that it is normalized, so no need to check whether it is normalized or not. Okay, there is no need to check whether it is normalized or not. Why there is no need to check? Because it is given that it is normalized. Okay, so normalized wave function of a particle is given like this. We have to find the expectation value of position, which had been asked to you in 2015, and this momentum part was not asked to you. The momentum part was not asked to you. I have put it deliberately over here. Okay, momentum part I have put deliberately. So you have to find out expectation values of this. Okay, these two things. Now our first step will be very obvious, as the wave function is normalized. So you will write it like this. Okay, as the wave function is normalized, so bracket psi. Okay, bracket psi will be equal to minus infinity to infinity psi star psi dx equal to 1, and it is one dimensional also, right? Why d tau has not come over here? Why d tau has not come? Because clearly your wave function is one dimensional, as is visible from the expression. It is visible that it is one dimensional wave function. Okay, so as it is one dimensional wave function, so dx will come instead of d tau. This is quite obvious thing. Okay, now we will find the value of basically n star n. Now how will we find the value of n star n? This has been solved in the previous classes. If you have made the notes out of previous classes, then this thing, that n star n equal to mod n square equal to 1 upon a root pi, this has already been solved. Okay, so I am not responsible if you haven't watched the previous lectures and have directly come to this lecture. Then I am not responsible for this. Okay, but let me give you a hint that you will basically put this wave function here, and after you put that wave function here, you will basically this for psi star it will become minus I, and for psi x it will remain plus I. Okay, so when you take the product, what will you get? You will get minus infinity to infinity. Okay, e to the power minus x square over a square n star n. Okay, dx is equal to 1 you will get, and from here you will put this n star n out of this integral, and then you will evaluate this integral. Okay, you will evaluate this integral. Which integral? This one. Okay, which integral you will evaluate? This one, this integral. Okay, and n star n you will put common out of here. Okay, so this is very clear from this thing. Okay, so let me, yes, so it is very clear. So wave function is normalized, so this is this thing, and from here n star n has been solved. Okay, now we have to find out the expectation value of position. Okay, so expectation value of position can be found out like this, that the formula you have already learnt, and in that formula one more thing was there in the denominator. In the denominator bracket psi was there. Okay, but that term clearly came out to be equal to 1, as it is given that wave function is normalized. So denominator of this formula has become 1. Now after you solve this, okay, so what will you get? Psi star x psi x. Okay, now x hat will become your x. Why will it become x? Because I had already told you that for position the operator is simple algebraic multiplication by x. So we are basically simply multiplying by x. Okay, I had already told you this, that for position and position vector operator or position in x direction operator, that operator simply means that it is algebraic multiplication by x. I had already told you in previous classes. So from there, over here also x will come, okay, in multiplication. So psi star will become your n star, this thing, okay. How? Because the value of psi has been given to you. The value of psi has been given to you. What is that given? It is given like this. The value of psi has already been given to you. And so you can basically take the star value, okay. You can basically take the star value, and after you take the star value, means conjugate value, complex conjugate, in that I will be replaced by minus I, n will become n star, okay. And this psi x will remain as it is, and in between I have forgotten to put an x, so put an x over here in between also, okay, in multiplication. So by laws of indices, this term will cancel with this term, okay, and it will become, what will it become? It will clearly become like this, okay. Expectation value of x equal to n star n integration minus infinity to infinity e to the power minus x square over a square x dx. And I have already told you that the integration of this term comes out to be equal to 0. This thing has already been told you in some lecture 7 or 8, I think, okay, if I am not wrong. In some single digit lecture, this thing has already been told to you that this function is basically your odd function, so its value will be 0. Why its value will be 0? Because suppose let this function be f of x, I am representing it with f of x, okay. So minus infinity to infinity f of x dx, okay. Now it will become minus infinity to 0 f of x dx plus 0 to infinity f of x dx. It will become like this, and eventually this term, okay, this term will be equal to negative of this, okay. That term will be equal to negative of this. So basically these two terms will cancel out, and after those two terms cancel out, it will yield you 0. So it yielded you 0. So n star n into 0 is equal to 0, okay. So your expectation value of x has come out to be equal to 0. Now what does it mean by expectation value of x has come out to be equal to 0? So what does it mean? Your motion, your quantum mechanical system is in one dimension, okay. It is along x direction only. It is one dimensional system. So expectation value of x has come out to be equal to 0. That simply implies that the probability of the particle being found along positive x-axis and of the probability of the particle being found along negative x-axis, both are going to be the same. So the probability distribution curve will be symmetrical, okay. Why it will be symmetrical? Because your expectation value of x has come out to be equal to 0. So suppose if there are 5 particles over here, okay, at plus x there are 5 particles, then means probability of 5 particles is there at plus x, that at minus x also there will be probability of 5 particles only. So that's why the expectation value of x has yielded you 0. That's how, okay. So the same thing has been written over here, that this result implies that the probability of location, because it is expectation value of the quantum system, okay. Expectation value of x means location x means that your particle is expected to be found in some x, okay, and that the expected values of those x on where the particle is likely to be found, the expectation has come out to be equal to 0. That means along the plus x and along the minus x there is no difference, okay. If suppose the case would have been different, then what would have happened? Suppose this would not have come to be equal to 0, suppose it would not be 0, suppose it is not equal to 0, then what will happen? That at x equal to plus 5 there are suppose 100 particles, but at x equal to minus 5 there are only 50 particles, okay. So there are 50 particles in surplus, okay. X equal to minus 5 has only 50 particles and x equal to plus 5 has 100 particles. So there are 100 particles in excess at x equal to plus 5. So the expectation value would have come out to be greater than 0 in that case, okay. But over here probability along positive x and negative x both is the same. So your expectation value of x has come out to be simply equal to 0. Okay, so like that you can understand these things. Okay, now this result implies that the probability of location of the particle on positive x-axis and negative x-axis are same. Okay, now the expectation value of momentum px is similarly we have to find the expectation value of momentum also, so we will find out that also. The expectation value of momentum px is, now it will be given by this. Okay, now I had already told you that momentum operator is not equivalent to multiplying by momentum. Okay, the expectation value of momentum you are finding, but over here momentum operator will come. So unlike the position operator, momentum operator does not imply that you are multiplying by momentum. Okay, momentum operator does not imply that. Okay, so you will replace it by momentum operator. So how does your momentum operator look like? Your momentum operator, one dimensional momentum operator, okay, it looks something like this. And as your system is one dimensional, so you will use one dimensional momentum operator. So after you put the psi star value, after you put the psi x value, okay, then you will take the differentiation with respect to x. I need not tell the differentiation. Okay, I need not tell the differentiation. Okay, so it will be basically n will come out. Okay, n will come out of this differentiation, and h cut by I will remain. Okay, and this thing will also be as it is. Okay, and this term in addition has come. Why this term has come in addition? Because when you will take the d by dx, all these things will be differentiated, and then this power will also be differentiated. So that power differentiation term has come over here, that power differentiation term. Okay, so basically you can have a look at all these things also. Okay, and keep on noting along with me. If you are not making notes along with me, then there is no remedy at my hand. Okay, there is no remedy at my hand. Then px operator expectation value, then again it will be something like this. Okay, how this has come, you can clearly see this thing. Okay, you will basically you know that integration is a linear operator. Okay, so as integration is a linear operator, you will expand this bracket. This term and this term will cancel out. These two terms will add by the laws of indices. Minus x square by a square will come. Okay, and after you expand this bracket, okay, after you multiply this term with the terms inside this. Okay, first this, let this be some k. Okay, not k, let us assume it to be m. Okay, suppose this is m, so m will be here, and m you will multiply with this first, and then you will multiply with this in the second instance. Then this integration will split into the first part and the second part. Okay, so the integration has clearly split into the first part and the second part. The first part and the second part integration has split. Okay, and what will this become eventually? This is an odd function. Once again this is an odd function, the value of which comes out to be 0. I have already told you. So this value comes out to be 0. H cut k remains as it is, this h cut k, and this term, okay, this term has already been told to you that in minus infinity to infinity e to the power minus ax square dx. Okay, I had told you to mug up the result, and the result which I had told you to mug up was square root of pi by a. This result I had told you to mug up. Now instead of a we have 1 over a square. Instead of a we have 1 over a square. So instead of a, 1 over a square is here. Okay, not 1 over a square is here, and over here also instead of a, 1 over a square will come. Okay, so the same thing has been written over here. Then after that this a square will go in the numerator and falana dimkana. Okay, so I don't think there is any need to tell you the further steps. You can have a look yourself. This n star n we had already found out that it is 1 upon a root pi. We had already found out, and h cut k is there, and this term will become a root pi. This term and this term will cancel out, and expectation value of momentum is h cut k. Okay, expectation value of momentum comes out to be h cut k. This is your final answer. Okay, So based on the similar concept, you can solve these two problems. Okay, this problem from the year 2002, and one more problem is there, this problem third number from the year 2005. You can solve these two problems based on the same concept. Okay, I need not tell those concepts. Now we will look at the next problem in the next class. Okay, because already the video is very long, and I am making the video through tablet, so it will take a lot of time if I keep on making the video. So let me stop the class.